Great. So today we're going to continue our discussion about data structures, algorithms. Well, we already covered all the algorithms. It's basically just how you do it on different data storage, data structures. In particular, how these fit into physical hardware. And I'll be introducing a new kind of tree today. I think I'll be assigning a homework this week that will be due next week. So I'll make an announcement on Canvas and I'll post it to Canvas. It'll be a PDF file. When you turn it in, please, I'd prefer turning things in through Canvas, and it makes work a lot easier if you turn in things as a PDF. If for whatever reason you have trouble with that, you can submit images, or you can also email me if for whatever reason there's trouble on Canvas. But I'll repeat, I strongly prefer PDFs submitted through Canvas. Okay, so let me go back with where we're at and where we're going. We've talked about what files are. We've talked about how to think of them as, in theory, really just a sequence of ones and zeros. And then you can interpret those ones and zeros pretty much however you like. And that's what an application does. An application is given a sequence of ones and zeros, and then it interprets those sequences of ones and zeros in different ways. Some applications might interpret it as an image, others as text or video, sound, whatever. We also talked about how files are stored on hardware. How it's stored on, just because I have them still, I'll put these things away. For databases, you can mainly think about these two types of storage. This type of hard drive, like a hard disk that has spinning disks in it, okay, not solid state. That's not very good for databases, because again, databases make sense when you're dealing with a very large amount of data. Because you're dealing with a large amount of data, you want to store it cheaply. I mean, if you use something like an SSD, it's going to blow up your costs. And the data structures that we talk about are, or that we'll start to touch on today, are optimized for this type of thing. So you have hard disks, and then you have memory. Memory is temporary storage. Things get loaded into memory while your computer is running. Your operating system, be it Windows, Mac, Linux, Android, iOS, whatever, they all work the same, will copy information off of whatever disk there is, and then load as much of it as it can into memory. Because memory, although it's temporary storage, it's like a working space for applications. So like when you are solving some problem and you bring out a bunch of like white pieces of paper so that you have sort of scrap sheets that you can work and do your calculations, and then once you arrive at the answer, you can just write the answer on the sheet, and then all of your sort of scribble notes and stuff, you can throw them out. You don't need to turn those in. That's sort of how memory works. So things are moved into memory there temporarily. If it's too big for memory, well, if it's one file that's too big for memory, well, I won't get into that. That's too much. But in any case, there is a back and forth. Like you can load up certain things from disk and load them into memory. If your memory is filled up and you need to load something else, well, then you'll delete things from memory, spin up the disk again, and then copy things from the disk into memory. With data structures, which is mainly what we were talking about yesterday, or Monday, I guess, and what we'll continue to talk about today, is a way of storing information. And these data structures are going to be what's called an index file. So you will have a data structure that is structured, and you can do things quickly on the data structure, namely insertion, deletion, and search. Those things, you have two benefits of loading it of having an index file. One, and I'll review this again, but whatever. One, the index file is small, much smaller than the amount of raw data. So small that you can load it into memory. And so that's fast. Also, because it's structured, then you can do all of these other things fast. Insertion, deletion, search. And and the raw data, you don't need to organize at all. So the raw data, you store it on disk, and it's not really organized on the disk in any particular way. Instead, you have a bunch of raw data on the disk, and also on the disk is a little index file. And the index file is a data structure. That data structure, that little file, gets pulled from disk into memory, and then you do your search and you figure out where the results are on the disk, and then you can read the disk for only those things. Okay, so you don't need to search through the entire disk, through all of this unsorted data on the disk, because you will have an index file, a data structure, that you can load into memory, and then you can figure out where on the disk is the exact information that you want. Okay, so that's all that an index file is, but it's hugely important. I mean, it's the reason why databases work quickly. You don't need to organize the raw data. So it's very fast to insert, potentially to delete, whatever. I mean, you can insert wherever you want, and then you just have to update your data structure, the index file. So throw however much big stuff there is kind of anywhere on disk, and update your data structure, which is where you're keeping track of where everything's at. Okay, so that's trying to pull together what the point of, or what one of the points of this sort of background in foundations is. How databases work, how hard drives and how things are stored on hardware, as well as some CS 101 things with algorithms and data structures. So today I'm going to continue to talk about the idea of encoding a tree in an array, because that's an important concept that previous semesters would have led me to believe. This is something that some students can struggle with. So I'll review that today and talk about how this is then basically an index file. So when you hear the word index file, you should think data structure. You should think a tree, mainly. And then I'll introduce a new kind of tree. So far we've talked about binary trees or binary search trees, whatever. And I'll talk about a more general type of tree. If you're comfortable with the concept of a binary tree, of a balanced binary tree, then it's just a little tweak here and there. I mean, it's not a big jump. So if you have questions about the way that a binary tree works, please raise them, because otherwise, when I talk about a slightly more advanced tree, you'll be more confused. Right. And so that will be mostly today. Some review. I'll talk about a new type of tree. I might be able to, I might describe this kind of tree, a B-plus tree. And this is very common in databases, and you use it for any type of structured data that you have. And then hash-based indexes, I don't know if I'll have time today for. We might have to save that for the next time. Your homework will be about data structures and algorithms, trees and search algorithms and things like this. Be careful in the homework. I'm not trying to trick people at all. In fact, I'm partly mentioning it now. Sometimes you have to be very careful about the way that you speak. So if I ask a question about a binary tree and I don't specify that it's balanced, then that could be a different type of answer than if I'm talking about a balanced tree. So keep that in mind. And yeah, before I go into reviewing stuff, are there any questions? Can we finish the pointer example from last class? Yes, I'll get there. Okay, no questions. So the last class, I felt like I was doing most of the talking, and I would like to, I don't know, give you guys more of a chance to speak up. So I'm just going to be choosing people randomly and asking questions for review. So how about, Caesar Esteban. That's a great name.
Hi, Professor. How are you?
I'm doing well. Okay, so the last class I was talking about how insertion and deletion on an array takes time n. And so therefore we have a reason to prefer trees, because you can insert and delete faster. I also said at the time that I'm kind of lying to you, because there is a way that you can still use an array for this. So why might some people think that this is a set rule? I'll say this is kind of a lie.
Maybe because they're unaware that you could encode the array. So if you don't know that, then based on the simple fact that it would take n steps as opposed to log n steps, it would seem that it's longer.
Yeah. So why in this example, you remember why I was saying that insertion would take time n, for example?
Because in order to modify, let's say in the worst case scenario, if you have to modify the first element of the array, you would have to shift all the other ones, unless if it's not encoded.
Right. So if you want to add a new element, you have to add it at the end. And I described why this was before. There is a technical reason for it. It's not just because. It's because of the way that programs are stored in memory and the way that those programs are allowed to grow in memory. I won't go into it again, but yeah, this is the idea, that if you want to insert something here, then first you need to create a new cell for your array. Then you need to shift everything over and then insert it at the beginning. That's the worst case. This would take time n. Great, thank you very much, Caesar. Excellent. Okay, how about Grant?
Hello there.
Hey. Um, okay, so uh, let's see. Yeah, we'll talk about the layer by layer way of encoding a tree. Can you remind us how that goes? I'll start a tree, I'll draw one, and then you can tell me how that would be encoded layer by layer. Um, how about that one?
So I believe layer by layer was the one that most people understood intuitively. So we would start with 50 in the array and then go 40, 60, and then I think the last value is 45.
Like this?
That looks good to me.
Okay. It's missing something. So, I'll remind you, in order to traverse the tree, so if we wanted to follow this path to get to the tree, because it's layer by layer, well, first of all, I'll remind you that you have to, for things with a tree, you always start at the root. You start at the root and then work your way down. Maybe there's other algorithms where you're going up and down and things like this, but you always start at the root. Now, so we know where the root is because it's whatever the first element of the array is, and that's at index 0. Okay, and now there's a simple rule that we can have if we want to go left or go right. Do you remember what that is?
No.
Okay. Index I. Go to left child. Go to right child. Okay, good. Well, we got part of the way there. Okay, Jonathan, can you unmute yourself?
Yes. How you doing?
Okay, doing well. So here, this is the rule. This is 2i plus 1. This is 2i plus 2. Okay, so let's start at the root, and let's keep it the way that Grant originally suggested, where we have this array. So on the left, that's the green path. That's the one that I want to follow. So I start at the root, which is at the beginning of the list. And now what?
So to get to the left child of
Mhm.
50,
Yep.
you do
This one.
2i plus 1. So it'd be 2 times 0 plus 1. And you get
Right.
to 40. And then to the right child, oh, you want to get to 45, right?
Right. So we do this, and now we end up with the number 1, which means that the left child is at this index location. Okay.
So then
Now we want to go right.
yeah, so
And
then you do
Mhm.
2i plus 2. So you're at 1 right now. So 2i would be 2 plus 2 would be 4. Index 4.
4. Okay. And of course, we're missing an index 4. I'm going to do this. So this is where the element should be. This is where 40's right child should be, but it's not. So how do we fix this? How do we fix the array?
So you need to have a full and balanced tree, I believe. So you would have 50 in the first in the 0th index.
Mm-hmm.
The first index would be 40. The second index would be 60. Third index would be a null. the fourth index would be 15, or sorry, 45, and the last two index would be null again.
Perfect. Right. So thank you very much, Jonathan. Perfect. So if you're doing the layer by layer method, you're always encoding a full tree. Okay, this is a full tree. And the reason why it has to be a full tree is because you're following this rule. And it'll screw up, as we just saw here, if you don't have null values, if there's empty spaces. If there's empty spaces in the tree, then you just need to create basically trash spaces in your array. That way you can maintain this sort of simple rule where however you want to traverse the tree, left, right, 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 left, whatever, you can use the same rule over and over and over. But in order to be able to enforce that rule, then you must encode a full binary tree. And where there's missing spaces in that full tree, and I'm saying a full tree here because here's null, this is null, and this is null, right? Every single space has to be filled. Same thing goes here. If I put the number 43, then here I'd have to have two more nulls, and then here, null, 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 right? So then I could extend this array with another 8 nodes, where it would read null, null, 43, null, 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 null. So this is really bad for unbalanced trees because you're having to encode a full tree no matter what. Actually, I'll keep that there just because it's to emphasize the point. Okay. Great. How about Indira? Indira.
Hi, Professor.
Hey, how are you?
I'm good. How are you?
Okay. So, I have sort of, well, I'm not sure how to describe the question. I'll just ask it. This here, is this an array or is it a tree?
I think I'd say an array because you start off by 0. Like it's a tree that's turned into an array.
Yeah, very good. Okay, yeah, that's basically it. I mean, this is called an encoding. So this is a tree encoded in an array. So technically speaking, it's an array. But like a program, when you look at this array, you should be interpreting it as a tree. Okay, so it's sort of both. I mean, it is an array, but it has a tree encoded inside of it. Okay, so it's kind of both. When you look at it, you should, if you look at something like this, in this case, you should be thinking of it as a tree. And so you don't, if you're searching through this, you don't start, left to right like this when you're searching through it, because that's really inefficient. Instead, when you search through it, you follow this rule. And so the way that that'll work, or the way that it'll look, I'll just kind of make a thing here. You'll be jumping in the array like this, exponentially further each time. exponentially further because the first layer only has 1 node, then you'll have 2 nodes, then you'll have 4 nodes, then you'll have 8 nodes, then you'll have 16 and 32. And so each time, that is to say, you do not, if you're encoding a tree layer by layer, you do not go left to right when you're going through this tree. Instead, you're sort of hopping in bigger and bigger and bigger hops. You move through this array using this route, okay? Where you're jumping each time to some new section of the array, okay? All right, I think that's enough for, let's see, traverse array this way. Okay. I think that's enough review on that unless there's any questions, in which case I'll pause for them. None. Okay. Somebody asked if I could finish this example. I'll just copy this. Well, what do I do? Okay. So the layer by layer method, which is up here, that's one way of taking a tree and encoding it inside of an array. Okay, it is an array, but you interpret the numbers like it's a tree, and therefore you get all of the benefits of a tree, even though you're using an array. We have to use an array, by the way, because that's how things are at the low physical level in computers. So, okay. But we can have the best of both worlds, right? I mean, we can have cheap devices that store things as arrays, but we can have all of the benefits of trees because we encode, we order things in a very particular kind of way in the array. And then because they're ordered in this very particular clever way, then you can do things faster. All right. So this, the more common way, and the way that we'll focus more on now, is the pointer method. And the reason why this is used more often, I guess, is because it's easier to maintain, and it's good for even unbalanced things. Also, this is very much closer to the way that B+ trees are stored in SQL, which is why we'll be focusing more on it. Now, it's just going to be a different way of taking a tree and putting numbers inside of an array such that we can traverse the tree. That we can move through the tree using an array. The way that this works is for every node in the tree. Oh, God. My eraser's not very accurate. It's fine. So here, for every node in the tree, you will have its value. That would be, for example, the value 10. And then you'll have a pointer to where in the array, the index of where that left child is in the array. So here I'm highlighting the node 10 in the tree. Also down here in this array, I'm highlighting 10 to focus on it. And let's say that we put 5 here. Oh. 5, and then 4 is an index 12, and then 20. And let's see, 5's right child is 7, which we don't have yet. Okay, maybe I'll ask a student for that. Put a placeholder here. Okay, so because we always traverse trees from the root, then we also have to have an extra piece of information, which is you have to have a pointer to the root. And that's just something you can save on the side. So that way you know where to start. Because there's no guarantee of where nodes are at in the array. They can be anywhere. It's kind of a nice thing. But you need to know then where the root is so that you can do other things. So in addition to having this array, we also have this root pointer of the number 15. That means that the root node starts at index 15, which is right here. That's index 15. And because our application knows that each node has this type of structure, then we know that this whole green area is that one single node. 15 is the beginning of it, and then the next two indices are going to be the index of its left child and the index of its right child. So let me get rid of that. Let's say, let me pick on a student actually. Let's see, 10, 20. Great. How about Kaitai? Is that right? Kaitai? Kaitai Yang. No Kaitai? Yang? All right, Karen.
Hey, Professor. I actually had a question. So,
Yeah, go ahead.
root pointer at 15, is that just like you chose it to be at 15, or is there like a reason that it's at 15?
So there's no reason why it has to be at 15. It's just wherever the root is, remember where it's at.
Okay, so it's not like a number that you chose. It's like the position that the root fell into.
Yeah, basically.
Okay.
Yeah. So there's reasons why this would happen, right? It's not like I'm just giving you a full tree and then saying, okay, store it. Or maybe that's how things begin. But then you're adding elements, you're deleting elements. The tree is remaining balanced. In fact, it doesn't have to, but whatever. If you're inserting elements and you're deleting elements and maybe reorganizing the tree and stuff, at some point, even if you start off putting nodes in very particular locations, those locations are arbitrary. That means that they're like that, but by accident. Like there's nothing special about those locations. So maybe originally, for example, 30 was the root. Maybe that was the very first element that was added or something. And then, I don't know, after a bunch of reordering the tree to make it balanced, node 10 now is the head, or is the root. Does that make sense? Or
I'm like kind of confused how this array gets started, like using the pointer method.
okay. I will make a note and I will get back to that. And I'll give an example of balancing a tree. I wanted to avoid it, but whatever. We can get to it, and it'll make this make more sense. I mean, I can give like a concrete answer. So I'll do that after this. Besides that, do you have any other questions?
No, I mean, I think that like my question is like I just don't really understand like this entire method.
This entire method. Okay. So let me see if I can come up with some sequence of numbers that work nicely. Okay. You don't need to know this for the class. Okay, what I'm going to describe. This is an algorithm for maintaining balance in a tree. Okay, let's see. Why not start with the root at index 0? Sure, you can do that, and in fact, we will do that in this example, but the root can change. So you don't want to start moving things around the array to always keep the root at 0, because that's a waste of time. I mean, you're going to be moving, now that's like shifting things around in the array, which makes things slow. And we don't want to shift anything. Once something's there, just keep it there. And then you can update other things. But you don't move things around.
If you were to always start, like before putting anything in, if you were to always start with the root at index 0, would it matter?
If you were to always start with the index at location 0, not really. I mean, you'd just be adding an extra step. So if ever the root gets updated, then you'd have to take the position of the thing that's going to be the new root, swap it with the thing that's at position 0, and then that way it's at position 0. It just adds one single extra step. So I don't know. If people preferred that, I guess you could maintain that. It's just not really necessary, I guess. But if you only did that and you only moved the root, then okay, yeah, whatever. That works. It won't really affect running time or anything like that. Okay. So here's what I'm going to do. I'll try to be quick because this is an aside, but I'm trying to give you like the real answer. Okay. So if you're given a sequence of monotonically increasing numbers, that means numbers that always just go up, for example, or they could always go down, either way. Inserting these into an array, into a binary tree, is like the worst thing you can do. Why? Because in a binary tree, if I were giving you these numbers in order, it would end up like this. Actually, I'll only do 7, just to make a pretty full tree. Right? But that's bad for search, because in the worst case, the depth of the tree is really large. And therefore, the longest path is also large. You want as shallow of a tree as possible, like I went into before. So, this is unbalanced binary tree. Okay, and that's inserting things in the simple way. You give me the number 1, great, I'll make that the root. Number 2, okay, that's bigger than 1, so I put it to the right. The number 3, bigger than 1, bigger than 2, it goes to the right of 2. The number 4, bigger than 1, bigger than 2, bigger than 3, so I'll put it to the right of 3. I'll come back to that question in a minute, Ellen. Okay, now, what if we wanted to build a tree, but we want to maintain that it's balanced? Then we need to have an extra algorithm. So the way that this will work is you insert wherever you want, but then at the end of inserting the place where it would go the most easy, you then update your tree. You have a balance algorithm. Okay, so there's an insert, there's a delete, search, and now I'm introducing another one, balancing the tree. So how would this work? It starts off the same way. put the number 1 here. Okay, no problem so far. Insert the number 2. No problem. It's still balanced, so we're done. Now we insert the number 3. Okay, now we have a problem because the tree is no longer balanced. So now we have to balance it. The way that this works is you look at the number 3, you see is it to the right or the left of its parent, and its grandparent as well. So you will, okay, hold on, let me do this real quick. How would this look like with the pointer method? So first we have index 1, null, null. Start from the beginning. Okay, there. We have our root. We've inserted the very first number. Okay, we don't know what's going to end up being the root in our balanced tree. In fact, the quickest way to figure that out is going through this algorithm or something like it. Okay, so we insert the very first number. Let me put my indices. 0, 1, 2. Okay, in the end, we'll have 21 indices. I might not go through this whole example. Well, whatever, we'll see. Okay, so here's how we begin, right? We insert the number 1. The number 1, we're encoding it as a pointer at index 0. It has no children, so each of its children indices are null. Great. Now we insert the number 2. Okay, no problem. We put 2 in the next available space. 2 now has no children, but we need to update where the child pointer is, and that's at index 3. So far, so good? Have I lost anybody here? No, great. Now, we insert the number 3. So we put 3 here, null, null, right? That's the easiest thing to do. Oh, and now we need to update where 2's right child is at index 6. Okay, but now we have another process where we are going to balance this tree. We want to maintain a balanced tree. For the sake of time, I'm not going to go into the specific algorithm, but you can just sort of see it here. Here, 2 should become the root, 1 should be the left child, 3 should be the right child. Now the tree's balanced. But do I have to move this whole thing now to be in this block? And then I have to move this block to be in this block. And then I guess the 3 I can keep. Right? Now I'm moving all of these things around. And that's going to take time. And there's no reason to move these, right? It's going to take it's going to take some extra memory, and I'm not going into some of the details, but right, easier than moving all of these things around would just be to update the pointers and say, okay, well, you know what? Now 2 has a left child, that's at index 0, and a right child still at index 6, and 1 has no children. No. Right, now I've had to update 3 locations, right? I just need to update 3 locations, and I don't need to move around 2 nodes, which would be at least 6. So I've saved at least half the work. And before I had this is the root pointer equals 0, but now I can just update that and say, no, actually the root pointer is 3 now. Now I insert the number 4. Here's the number 4, null, null, have to update 3's right child to be index 9. And it's still balanced, so still good. You insert the number 5. Now it has no children. 5 becomes the right child of 4 at index 12. Let me read that in a different color. At index 12. But now the tree is, again, unbalanced. And I'm not going to go through the algorithm, but it's not too hard. You could probably figure it out yourself. It would update to be, 4, 3, 5. Now we have a balanced tree. And at most, we will need to update like 2 nodes or 3 nodes pointers. So that's 4 or 6 different indices that you'd have to update because now their children are different. Here, I'll go ahead and update these. So I'm going to move things around my screen so I can see. Okay, so 2 is good, 1 is good. Node 4, we need to update because its children have moved. 3's children now has no children, and 5 still has no children. So that's 1, and then that's at index 6, and that's at index 12. There. And our root pointer can stay the same. How do you know when do we enter a position number and when do we enter an actual number into the array? So the application, or you know, because, well, you just take whatever you think and the way that you figure it out and code it. And so that is the algorithm, but whatever. This program understands that this is the value. This is the left child pointer. And this is the right child pointer. And this will point to the value of left child. And this will point to the value of the right child. And so you just know this. This is the way that the array should be organized. Otherwise, your search algorithms, insertion, like all of them make no sense anymore. Like they'll break. They'll break in a similar way as if you don't have null values in the layer by layer method. You have to have the null values because you know that you're going to be traversing it in this way. And in order to keep that rule, which is just the rule that the algorithm follows, then you have to have these null values. Similarly, you know ahead of time that this is the way that each node is going to be encoded. So when you have the root pointer at 3, then you know that's going to be the value, the number 2. And then the next 2 things, that's going to be the index of the value of the left child. And the next one is going to be the index of the value of its child. So if you go left and you want to go here, follow this, then you know that that's the value, and then the next 2 are going to be pointers, just like this, because everything should be organized this way from the beginning, and that's maintained. Okay, so in any case, this is the reason why. If you, I don't know, maybe, sure, if you want, always put the root at the beginning, but then you're going to have to be swapping things around. If you only do that for the root, no problem. I wouldn't care. I don't think any company would really care. Just, I don't know, because you like the number 0. You like the root being at the beginning. But just don't do that for the rest of the tree. Because as soon as you start swapping all of these things around, you're wasting a lot of time. That's the reason why this is bad. If you try to organize, if you try to sort your data from smallest to biggest, then when you try to insert, you could end up wasting a lot of time maintaining that type of order from smallest to biggest. So there's a different way that you can order the data. You could order it layer by layer, or that's the way that you interpret it, right? I mean, if somebody looks at, these numbers here, in what kind of order are they in? It's not biggest to smallest. It's not, well, you're going to interpret it as a tree that's encoded layer by layer. And so now when you look at these numbers, you see a tree. You don't see like a sequence of random numbers. These numbers aren't random. They're placed there in a very specific way, such that when you look at it, you know that it's a tree, a binary tree. Similarly for this, let's go back down here. Similarly for this, except here, the order doesn't matter. Maybe that's the mental block to try to get around. It doesn't matter what the order of the nodes are here, because the way that you're traversing is by pointers, and pointers can point anywhere. It can go backwards, it can go this way, it can go left, right, it can jump, it can jump one position next to you, or it can go a billion positions the other way, just because it's a pointer. I mean, it can point anywhere. And because you can point anywhere, it doesn't really matter where you're putting whatever it is, because you can always just update your pointer to now point to that place. Okay. Okay. This is a little bit more detailed than you need to know about things. Like if you don't, but this is the reason why. I mean, it's an actual reason why. Because for other algorithms, and I'm not talking about how to balance trees, okay? That's a separate conversation. You don't need to know that for database management. You can know that there exists an algorithm that can do it. You could probably figure this algorithm out by yourself if you just sat down and played with it. Otherwise, you could just Google, search it or whatever. It's not that hard. But because it's valuable to have a balanced tree, then it's because that minimizes the depth, and therefore it minimizes any search. You will avoid really bad situations like this if you maintain a balanced tree. Then it's a good thing for insertion and deletion to have this balance method that it can call. Every time you insert, after you insert, call the balance. After you delete, call the balance. And that way you maintain the balance of the tree. And that works out well for the pointer method because it doesn't matter where things are located. It's an accident where they are. Here, y is 1 at the beginning because maybe when we were very first building a tree, that was the root. But that doesn't mean that it's the root now. Is this, because this node is here, is that important? It's an accident. If it seems, you should not get meaning from it. Because if you assign meaning to it, then you have to maintain that meaning, and that can get expensive. So, okay. I think that's good enough of a tangent there. If you still have questions about this, you can ask me after class, but I want to get to some other things. Let me see if There's some other questions that I missed. Right. The values of the left child and the right child are always indexes. Yes. Yes. That's what it means to be a pointer. Again, it's still a number, but now you interpret this number as the location in an array. And therefore it is defined as being a pointer because it points you to an index. There's nothing special about the number. It's all about the way that these numbers are interpreted. And if you're encoding a tree like this, then you can say, this is the interpretation that I want to have, and that's the one I'm going to maintain, and you do it. And, insertion, deletions, all these things are fast. In fact, insertions here, no, that's not quite right. I was going to say insertions are constant, but that's not quite right because you need to update pointers. It'd still be log n. Let's see. Can we skip that space 20 in the array until we encode 7 and then put the index pointer in position 20? Yeah. Let me see here. I think you're talking about this one. Yeah. No, you can't do that. She's saying, can you skip spaces? I mean, technically, if you're using this pointer method, you can put the nodes anywhere you want. I mean, there can be blank spaces and stuff like that. It's a waste of space, but it's not going to break the algorithm because it's all just pointers. So if you decide to insert something and then you skip, I don't know, 10 cells, and then you insert the next node there with 10 empty cells in between, well, the pointers are just going to jump past it because you're following the pointers. That's the way that you're going through the indexes of this array. So you'll just skip past the empty spaces. You're not going to be going from left to right.
Professor?
Yes.
Like what I meant by that was, so we put in like in space 18, we put in 5 because that's where we were. So if we look at like first the left child, we see that we already put the left child in at position 12. So that's 4. But then if we scan the array, there is no 7. So what I mean is, like, can we skip space 20 because we have no 7, and then just
I see.
once we encode the 7, we'll insert the pointer there. Just
Yeah,
because
that's
we yet.
yeah, basically. I mean, so in the beginning, maybe 5 doesn't have a right child, and then it's null. And now when you insert the number 7, which has null and null, then you would update this pointer with the number 21.
Okay. And it
Yeah.
it doesn't matter. We can do the pointer. We can do the nodes in any order.
Yeah,
Okay.
yeah,
Thank you.
sure. I mean, probably if you're given a tree, you might just, I don't know, do it layer by layer. That's the way that you're initially going to encode the tree. But after that, values could be deleted. If you delete a value, you don't need to shift everything. That can just be empty space. And now when you insert a new element, you can put it where that space used to be. Or maybe you're just adding, in which case you have a nice, pretty layered by layered tree. But then when you add elements, then you can just add them at the end in any order, and it doesn't matter. That's what I mean by it being an accident. If there is an order, it's not that there can't be, it's just that it would be an accident. Or maybe it was convenient in the beginning to do it that way, but you can't exploit that order in any way. So don't bother maintaining it. If you tried to maintain it, it would be worse because you'd be wasting time. Okay. Any other questions about this pointer method? Okay. Why in this example did I start with the number 30? My only goal of that was to emphasize the fact that order does not matter in the pointer method. So yeah, I probably could have written it down for an example in some kind of order just to make it easy, but I wanted to emphasize the fact that order doesn't matter. So I just started putting in things randomly. Okay. Just a moment. Ah, yes. Okay. All right. Now, I want to talk a little bit more about what I was saying at the beginning of lecture about having all of your data sort of unorganized. Your raw data is unorganized on the disk, but then you also have a small file that will be used for the index, and that file is a data structure. So I'm just going to make up some like arbitrary data. Okay, we'll say student ID, student name, student age. All right, whatever. Whatever, and their ages, I don't care. Okay, so whatever. Let's say that this is some data that we have, okay? Now, there's no order to this, right? The SIDs aren't in any particular order. The names aren't in any particular order. The ages aren't in any particular order. So this is the way that the data would be stored on disk in its raw form, okay? Now, what do I want to say here? Let's say we wanted, so this is, by the way, sometimes this is called a heap file. That just means unstructured. Unordered. Okay, so you have a heap file. That's just the name for all the raw data. And then you'll have an index file. Okay, here, let me pick on another student. How about Muskan? Muskin.
Hi, Professor.
Hey, how do I say your name?
Muskan.
Muskan. Okay, very good. All right. So we're going to do two things here. First, this is going to be by name. Oh, sorry, SID. Okay, so I want to create a, and here's index 0, 1, 2, 3, 4, 5, 6. Okay, I want to create a tree where things are ordered by student ID, a balanced tree. Are these numbers few enough where you can just tell me like what the root is and stuff? Another property of the root for a full tree, is that it's the median number of all the numbers. So like if you're given a big list of unordered numbers and you want to figure out what the middle number is, build a tree, look at the root, that's the middle number. And then, each way down you could see like, the median of all the data, the median of this half and that half and whatever. But that's a shortcut of where to start. What's the middle number here?
Maybe 10.
10. Okay, let's try it. All right. Okay. And
Okay.
so,
On the left, you could put probably 4.
okay. Sure.
And then on the left of 4, you could put 2, and on the right, you could put 8. And then on the left of the 2 goes 1.
It's not going to quite be balanced. Put 8. Let's see. Put 42 here, and then 8 here.
Okay.
And then 2 and 4. 2, 1, 4. Okay.
And then on the right goes 100.
Mm-hmm. Great. Okay. Oh, another thing. Let's see. Actually, can I change this color easily? That'd be nice. Cool. Okay. Let me erase these bubbles. So, what this node is going to be is SID index. Keep.
Professor, I have a quick question.
Yes.
Why 8 can be can be on the right hand side of 10? 8 is smaller than 10, right?
Oh, wait. I'm sorry. Yes, you're right. Let's see. So 8 needs to go here. 8. Thank you very much. 8, 10, and 4. Nope. 8, 10. Which one am I missing? 42.
42.
42. Okay, is that, let's see, no, then that's not 4, that's 8, 10. Okay, that's all the numbers. And good catch. Thank you. Okay, good. That's a valid binary tree. Oh, whoever that was who was just speaking. I want to create the nodes actually like this, where the first number is the SID. I'll write that in black. And then the second number is going to be this number that it corresponds to. Who was it that was just speaking? Okay, well, I'll think on somebody else then. How about Purva?
Yep. Hi, Professor.
Hey. So do you know what I'm asking?
Do you mind repeating it? Sorry.
Sure. So each node here, I want to be in this form, where the first number is going to be the SID, and we already have those. And then there's going to be a second number that is going to be the index. So each of these will have 2 numbers. So for example, the number 8, the SID 8, is at index 1. Make sense?
Yeah, okay. So for the next one, 42, would it be 6?
42 is 6. Yep, great. You got it?
Mm-hmm. And then next one would be 2 and 5.
2 and 5. 2 is not at 5. Here's 2.
Oh, I meant for like 10, it would be 2.
Oh, okay, I see. 2 and 5. Yes, okay, I got you. Yeah, all right. Okay, and how about the left side?
For 2, it would be 3. And
Yep.
then for 1, it would be 4. And then for 4, it would be 1.
4 would be 0, actually, but yeah, good.
Oh, sorry.
Yeah, perfect. Okay, thank you. All right. Does everybody understand this tree on the left, what it's representing? Maybe I'll do this just for added benefit. So 1, that's a pointer to 1. Here, that's a pointer to 6. That's a pointer to 5, etc. I'm not going to draw the arrows. Okay? Okay. Now, okay, so here is all of our unordered data. And maybe this has, I don't know, let's say like 1 million and like 1 million different things about these people, right? So this just goes, on and on and on. It's a lot of data about a lot of people, okay? So on the right, the heap file, that's a really big file with lots of names. They're, ID, name, age, favorite color, a list of all of their favorite shows in order, every single book that they've ever read, a name of all of their friends on Facebook, and then their friends' information, and whatever. This table is really, really long this way. Okay, going across. So imagine that's like a gigantic amount of information, and there's no order to it. Is this ordered by the SID? No, they're just kind of in a random order. Is it ordered by name? No, it's not in alphabetical order. Is it ordered by age? Nope, that's just kind of in random order. The table on the right is unordered, okay? And that's the raw data, okay? That's, you can just, when you have a new piece of data, where do you put it? At the end, there. I don't know, wherever is the next empty space on disk. Is it important where that is on the disk? Not at all. Just, put it wherever it can fit, and that's where it'll be. And then whatever that index is, I guess in this case it would be 7, you would update your tree, and now you could put, I don't know, the new number here. I don't know, let's say that's number, I'll also call it 7. That would be here. 7 is coincidentally at location 7, and whatever. New entry. It has an age of 42 and lots of other information. Okay? So for this gigantic amount of data, it's unstructured on the disk. Now, here in the index file, again, the index file is just a data structure. Here it's a tree. Now, that is very small compared to the heap file, because the only thing that it's made up of is the SID, and here that is the index. See, I'll do this. and the index equals SID. Not to be confused with, okay, sorry about this, but it's the way that it is. Terms get overloaded. So when I use the word index, it's different when I'm talking about an array. Their index means the location in an array. In databases, the index can be the key. Whatever. I'll just do this. I'll use the key. Key. Okay. It's called an index file. It's also an index. Whatever. Great. So the reason why the index file can be so small is because it's only storing these two pieces of information. That's it. You don't need anything else, right? So all of that information is here. So this is very small. Okay. Now, when you need to find a student, or if you need to find somebody by their SID, you can start at the root and you can traverse. And in the worst case, it will take you log n time, n being the number of entries that you have. So if this is a really, really long table where, I don't know, that goes down to 1 billion, then n equals 1 billion, whatever, this just keeps going, right? Then log n of 1 billion is like 9, 10, whatever, call it 10. Then even though this amount of data, you have 1 billion entries each with 1 million columns of information about them, it'll take you 10 steps to find anybody there, or to find any entry. And when you get there, where is, like, maybe if I want to find the number 10, I know that that's at location 2. And so then I can just jump to location 2. I don't need to search, from the top to the bottom all the way through all this data. No, I take a little tiny file, and then I can traverse it and find out where in this mountain of data that's just everywhere here, where exactly it's at. Okay? Okay, I didn't get to talk about B trees today, but that's okay. They're pretty short. Yeah, okay. Yeah, it's basically in the class, so thank you guys. I'll hang around for a few minutes if you guys have questions. Otherwise, have a good week and weekend.
Professor?
Yeah.
Would you actually just be able